we're going to get started in about 2 minutes. Okay, welcome everyone to our final live session. And I wanted to start off by opening the floor to questions that you might have about any of the assignments that are outstanding, including the SAS assignment that you're maybe currently working on. Hopefully the instructions were clear. What I was hoping that you would do is simply take the code that you were provided and run it in SAS, get the output, and interpret the output. So is there anyone who would like me to go through any of the aspects of the homework, the SAS 2 assignment?
Hi, Dr. Cook. Can you hear me okay?
Yes, I can.
Hi, it's Dan. I think I understood it pretty well. I think the only time when I got a little kind of, I don't know, unsure of maybe what I was answering was that last question.
Okay.
When I got all the way down to the bottom.
Okay, let me pull the assignment up. Sorry, I'm just doing this. Okay, just disappeared on me. Here we go.
The rest of it seemed pretty straightforward.
Okay. I'm going to go to stop share and screen share. Okay, can you all see the assignment now?
Yes.
Okay, perfect. All right, so just so I'm clear on which one we're talking about. And I'm happy to walk through any of these. And maybe I should walk through just to make sure that we understand what we're looking at. But Dan, was it number 5?
It was, but I'd be happy to walk through the whole thing if you're willing to do that.
It might help to build up to that a little bit. It shouldn't take too long for me to run this. Okay, and we haven't had enough really hands-on with SAS. It's really hard to squeeze it into 4 weeks. So I do want to take this opportunity to just kind of give you a little more background on how to do this. So really what I'm doing is giving you code to run SAS programs. In a SAS program, and let's just look through this first question. Determine which of the following risk factors listed below are associated with the outcome variable status, which the outcome is, the variable is called status, which is kind of an unusual name, which and it's either alive or dead. So this was the Framingham study, which they followed people at this point, probably 20 years, 30 years. And they're following this massive cohort and determining who died and who didn't. So this is, the outcome here is simply death as an endpoint. And we're using a 2x2 table to see what is associated with the outcome. Okay, and so normally we would do this maybe as a table 2 in a manuscript when we've described our entire sample. Now we want to know what things in a bivariate way are associated with the outcome. Another way of saying that is sort of what is the crude association between different factors in the outcome. Okay, so this proc-freq statement, which simply stands for proc frequency, is a very commonly used command in SAS. And oh gosh, let me start recording this. Oh no, it's automatically recording. Good. Okay. So the proc-freq statement not only runs frequencies, but in this case, we can run 2x2 tables. And if you think about what a frequency is just a count, right? It's counts and percentages. And we're adding to it in the second line, this tables command, which basically sets up our 2x2 tables. Basically, we're crossing frequencies, right? So we have 2 categorical variables, each of which have 2 values. And so because there's only 2 values, it'll end up being a 2x2 table. It really depends on how your variable is coded. If I had age as one of my variables, then my table would be very long, very tall, and perhaps very narrow. But in this case, I've dichotomized everything, or everything else is dichotomized. So it makes sense to run a frequency. And what often you try to do in programming is make it as efficient as possible. So instead of me writing 1, 2, 3, 4 different proc-freq statements for each of the independent variables, I chose to put them all in one array here. It's actually going to perform each of these as if I wrote 4 separate proc-freq statements. Okay, so even though it looks like I'm creating some, it looks maybe more like a multivariate thing that I'm doing, it's actually repeating this for each of those 4 variables. Okay, and there used to be kind of a premium on having your code be efficient. I favor having your code be interpretable. And so I wouldn't fault anyone for having 4 separate proc-freq statements repeated with each variable separately, only because it helps kind of guide the person who's looking at the code to say, okay, this is what this step is doing, this is what that step is doing. And especially if they were maybe not as familiar with stats coding, they might think that somehow this is a multivariate model. Okay, so this is not a multivariate. I'm just repeating 4 2x2 tables. And each of these is going to be crossed with status, our outcome variable. So this is a very typical command in SAS. And then the things that happen after this backslash, or is it forward slash? I can never remember which is back and forward, but you can see it. I'll call it forward slash. These are the specific options that I'm asking for in this statement. So the chi-square, if I wanted to produce chi-square statistic, that's the chi-square. There's no percent, no call, no cum that means that's no cumulative, no column frequencies, no total percent. It is going to give me row percent. So by default, it'll give me row percent. If I didn't want row percent, I would put in no row, just like it says no column. Okay. I've created the SAS code to basically answer the questions that follow, which is what we really want to know. Is there an association between weight status and being alive or dead, cholesterol status, alive and dead? And these are all separate 2x2 tables. So let's take this code, and I'm going to copy this just as you probably had to in your homework. Do this, and let me open up. Okay. Now it's a little strange in the visual programmer mode, because when you do commands over here in tasks and utilities, it's not going to really let you edit the text that it generates over here, the code. So if I go in here and set up crosstabs, sorry, there, I went right past it. I didn't. Sorry. There we go. Table analysis. So if I were to go in here and interactively do this, notice I had to tell it the data set that I want to work with. If I were to generate, code over here, it's not going to let me edit it over here, which is kind of annoying. I'm not sure why it has that. But what is nice about this visual programmer mode is if I make changes interactively, it shows up over in my command. So this is a good way to learn how to program in SAS because you can see what changes over here. So right now I have sex against nothing. And then as soon as I add status, okay, it's a little hard to see if I'm in the way here, but now it's actually put sex by status in here. But like I said, I can't really manipulate that, which is a little annoying. So what you need to do is go up to where it says new program. Well, it doesn't say that. There's just this little new button right next to where it says visual programmer. And I'm going to do a new SAS program. If I'm creating a new SAS program, it's going to allow me to edit it normally, meaning I can change whatever I want. So if you found that you're trying to do it in the original, you're going to hit a barrier there. Okay, let me move this out of the way. So hopefully it'll cut and paste what I already put. Beautiful. And nowadays, SAS is nice to us, and it actually color codes. And you can kind of get a sense if things look right because of the color coding. Notice if I were to remove a semicolon from this line, oops, no, it didn't mind that. Let's see, if I remove this one. Oh. Yeah, so when I remove that semicolon, the run statement is no longer in dark blue. But if I add that semicolon back, the run statement's there. So basically that run statement, until I put that semicolon, was going to be not interpreted correctly. So not to confuse you, but the color coding is helpful. It kind of makes you aware of if you've done syntax correctly. And that's just a matter of practice, okay? But it looks good. I'm going to run this. And again, instead of in interactive mode, what I'm doing here is I'm invoking a data set, SAS help.part. I'm telling it to create 2x2 tables against status, giving me chi-square tests and percentages. So I'm going to run that. Okay. And the output can get a little bit unwieldy because it's going to be, and that's another reason why maybe you want to generate 4 different statements separately. But it's going to go one by one. We have cholesterol status. Oh, and actually it's not even a 2x2, it's a 3x2. We've got borderline desirable high cholesterol, our chi-square p-value, okay? So don't forget, you can run a chi-square test for 2x2, 3x4, 4x6. It doesn't matter how many categories you have. It will appropriately calculate. But you do want to make sure that your data is appropriate for doing a chi-square test, that it's not actually ordinal, which this kind of is, but I'm going to ignore that for now. So this is the p-value associated with this chi-square test is right here. Chi-square p less than 0.0001. Okay, so that's for the association between cholesterol status and being alive or dead. Okay, so right now I'm just asking, is there an association? I'm not even asking anything about the direction of association. Looks like it's always a good idea to look at your output. So having high cholesterol, 47% had passed away. Those who were borderline, 36%, and that had desirable, 28%. So you can see pretty much a dose-response relationship between desirable cholesterol, borderline cholesterol, and high cholesterol. Believe it or not, this Framingham study done 40 years ago, or was started 40 years ago, is one reason we know cholesterol is bad for us. And that's one reason we test for it through this long-term follow-up. Okay, so yes, cholesterol is associated with all-cause mortality. Okay, and so if I go further down in this output, we shall see, oh gosh, it's so touchy. Okay, and then the next one I did was smoking status. Oh, and I wanted to point out real quickly with this one, notice that it goes borderline, then desirable, then high, which is a little weird. You would think it would go desirable, then borderline, and high. SAS is stupid. By that, I mean, it has rules that it's going to follow. And in this case, it organized these from alphabetically. So borderline happened to fall alphabetically before desirable, which falls before high. So obviously the rank order would be, doesn't make sense. You have to be really careful with that, with SAS, that if you have labels that they're going to be alphanumeric sorted. There are ways to change that. And I would recommend also maybe assigning a numeric value to these so that they are put in the order that that you want them to be. Okay, so that's really important to consider. So if I go down to weight status, okay, it all kind of runs together here. So the first portion of output is here. The second portion of output starts here. Weight status, normal, overweight, underweight. And you can see the p-value here is also statistically significant. And just like before, well, this is a little harder to argue, which you've got healthy weight, basically normal weight, 31% mortality, overweight, 41%, and then underweight, so it's like a BMI under 18, around there, 37%. So being either underweight or overweight was predictive of mortality in this cohort. Okay, so to make a long story short, yes, weight status is associated. Okay. Moving on now to smoking. Here's another example of where the categories get really funky out of order because of the alphabetization. So it goes from heavy to light to moderate to non to very heavy. You can see the very heavy smokers, 50% mortality, heavy smokers, 42% mortality, moderate, 37%, non-smoker, 35%. Oh, the light smokers are gonna love this, 32%. They're actually lower than the non-smoker. That is not to encourage you to go light smoke. There could be confounding, there could be random a fact, or maybe there's something there. But overall, you can see from non-smoker to very heavy, there's kind of a gradient. But really all we're testing here with a chi-square test is to say, are the groups different? And yes, indeed, they are very different. P-value, again, is this first chi-square statistic. P-value less than 0.001. And okay, so smoking, weight, cholesterol. What did I miss? Oh, blood pressure. Okay. But you can guess how this goes. This is another one where the category order is awkward, high, normal, optimal. Oh no, I guess that word goes okay. Optimal is at the bottom, normal is in the middle, high is at the top. So having high blood pressure, 51% mortality, normal 30%, and optimal 21%. And don't forget, this is people who were in this study for a very long time. So this is not like predicting the proportion who die in a short time period. This is just who died over the course of the study. But you can see again, kind of a dose response here of blood pressure status, weight, smoking, cholesterol, okay? So all of those things are associated. And hopefully you can figure out in question 1, is there an association with each of these, alive versus dead? Yes. Okay. And you're all like, ho hum, we all know these things are bad for us. At the time this study was done, we didn't know all this. I mean, we had suspicions, but we didn't really have definitive cohort epidemiological evidence, especially things about diet, cholesterol, high blood pressure. This was some of the first evidence in terms of health risks associated with some of these risk behaviors. So historically, this is very interesting. It's obviously not cutting edge science at this point, but all right, so yes, it is associated. So as you might guess, there could potentially be some kind of confounding among these different lifestyle factors, okay? Doesn't mean that everyone who has a poor diet, which might be indicated by cholesterol status, has weight issues as well, or has high blood pressure as well. But these things kind of commingle a little bit. There's some overlap among these risk factors. And so what we want to do is address potential confounding among these exposures. We're not really interested in effect modification per se, because it could be that, yeah, having both has like an additive effect, but that you can see with just by adding the two risks together. If you thought there was some kind of multiplicative effect, meaning like it's even worse than you'd expect if you had two, then we might be interested in effect modification. Okay, so now we're going to determine in question 2, determine which of the risk factors listed above that are associated with longevity or status death are also associated with smoking status, okay? The reason I'm having you do this, and I should have maybe been more explicit, is I'm interested in smoking. I'm picking that out as kind of my main factor of interest. I want to know, well, okay, are these other variables, weight status, cholesterol status, blood pressure status, that we know are associated with the outcome, are they also associated with smoking? Okay, that's going to tell me if it's a potential confounder, because unless it is both associated with the outcome and the exposure of interest, in this case smoking, it's not going to be a confounder. Okay, so they have to be associated with each other and with the outcome. So that's kind of step by step why I'm taking you through, that's why I'm doing this. So same logic with the code, okay? I now change, instead of the outcome, I'm putting smoking status as my column variable and putting cholesterol status, weight status, and blood pressure status. So I'm gonna copy and paste that into my little thing here. And so navigating this, notice that if the code doesn't appear, you just click on the code, go to my results again, code. Okay, so there it is. I'm going to just paste it right below here. I don't need to create a fresh program. What I could do is put annotations in here and say, hey, this is to test association with outcome. That was a bad. Oops, what did I do? Okay. So I commented out, that's why it appears in green. Okay, so it's always a good idea if you're going to share your program with someone else to kind of put these notes, but I won't do more of that. Okay, so I'm just going to run this sucker right here. Okay, so this is kind of like step 2 for testing to look at potential confounding. So now I'm looking at cholesterol status and it's associated with smoking. Notice now I have a 3 by 1, 2, 3, 4, 5 table, okay? But it is, in this case, we're gonna look at this p-value here. P equals 0.1485. It does not appear that cholesterol status is associated with smoking status. And you can kind of see that here if you just eyeball the proportions. Notice that among the heavy smokers, the proportion who are or the distribution, like 20% of those who are borderline or heavy smokers, 20% who are desirable or heavy smokers, 20% who are high cholesterol or heavy smokers, and the very heavy smokers, you can see they're very similar. And so it's not that surprising that the p-value here is not statistically significant. So, but it's always good to check to make sure that it makes sense. There aren't actually huge differences, that maybe you set it up wrong. But here we go, p-value. So cholesterol is not associated with smoking status. Okay. In this sample. I don't know if it is in the population. Now we're looking at weight against smoking status. Notice highly statistically significant, or I'll just go ahead and say statistically significant. P-value, again, I'm going to look at my chi-square test. P less than 0.00001. And it's always a good idea to eyeball it. You can see that heavy smokers are less likely to have overweight, which actually makes sense. There is an association here, though. What is the association? Non-smoker. So actually, non-smokers are more likely to be overweight, which actually is consistent with what we know. People who smoke sometimes do lose weight or are normal weight, even though they smoke. Okay, so anyway, there is a statistic. All I'm really testing for here is a statistical association. And then blood pressure status and smoking. Yes, there is a relationship, okay? And at this point, I'm really just testing to see if there's potential confounding, and the criteria would be that it's associated with both the outcome and the exposure. So let's just remember, blood pressure wasn't, I'm sorry, blood pressure was, weight was associated, but cholesterol was not, okay? So notice there's only 3 now, because I'm asking, are they associated with smoking status? Okay, so that's number 2. Hopefully you caught that. So based on questions 1 and 2, which of the following variables are potential confounders of the relationship between smoking status and the status variable alive versus dead? Okay, so again, to be a potential confounder, it has to be both associated with the outcome and with smoking status. Okay. So I'll give you a hint on this one. One of these is not a potential confounder. 2 of them are. One of them was not associated with smoking. Like we're playing Clue here. Okay, so that was that. That was to say, okay, are those potential confounders? Okay. So now I'm moving into a multiple logistic regression model. And in the lecture, I've tried to make it clear that there's a nice connection between running 2x2 tables and doing chi-square tests with a dichotomous outcome and doing logistic regression, because often we can explore relationships using just simple chi-square tests, understand the relationships, and then move towards this fancier model, okay? And it makes it a lot easier also to interpret the direction of the coefficients and things like that, make sure everything's set up correctly. So I always recommend not just jumping in to the model first. So here we go, proc logistic. Now we're getting real fancy here. Now we're into the graduate level statistics here. So proc logistic, not that the other stuff wasn't, but mostly joking. But this is a fairly powerful tool. What I'm doing here, and let me copy it into my code window. Go back to here. Don't forget, I'm in results view, so I'm going to go back to code. Again, I can just plop it down here. You can think of a program as kind of a worksheet, as long as you are only running portions of it. I wouldn't want to keep running it from the beginning, but if I run this section. So this structure is proc logistic. Okay, so I'm doing a totally different procedure here. I'm actually running a logistic regression model. And some of these statements within here, you might not intuitively understand what they mean. It would be a lot more intuitive if you plug these into the logistic regression. You would basically say, what are my covariates and what are my variables? Okay, so we have here our outcome is status. Okay, so in this model statement, I'm going to ignore the class statement for a second. In the model statement, this is where I'm saying, okay, well, what is my dependent variable? It's status. What event am I interested in as a yes versus no? Alive. Okay, it's giving me the choice here of, do I want to know the likelihood of being alive or the likelihood of being dead? They're not exactly the same, or they're the flip of each other. So in the syntax here, you have to specify which outcome you're interested in, which is kind of nice. Normally we code it, the event of interest numerically 1, the event of non-interest is a 0. But in this case, we actually have text. So we'll say alive. And then we have 2 variables in our model, smoking status and age at the beginning of the study, age at start. And that's really the meat of the model. The class statement is something that it did automatically. It recognized that smoking status is going to be treated as a categorical variable. The link has to do with the fact that there's a logit link function, which is mathematical. This was all generated by SAS. as part of the proc logistic statement. All I told it was, what's my outcome? What are my two variables? Okay, so I'm going to run this. And logistic regression has kind of a lot of output. But what I'm really interested in here is, well, there's a couple things I'm interested in. Well, I'm going to go right down here. Okay, so it's treating smoking status categorically. And we've got separate dummy coded variables for very heavy smoker, moderate smoker, light smoker, and heavy smoker. The reference group here is very heavy smoker. Okay, you could have flipped it. You could have flipped it in the way you code it and made non-smoker the reference category. But in this case, our outcome is being alive. Okay, so we're looking at what predicts living. So when we look at these odds ratio, light smoking or here especially non-smoking versus being a heavy smoker increases your odds of survival by 3.7. Okay, that's how you'd interpret that. Being a light smoker versus a very heavy smoker, 3.107. Being a moderate versus very heavy, 1.9. And being heavy versus very heavy, 1.5. Okay, so whenever you have a categorical variable in a logistic regression model, there's always a reference group. Okay, so if I had just put sex in this model, we would have one odds ratio estimate for, let's say, male versus female, right? In this case, the reference is very heavy smoker, and I've got risk estimates for each of the categories. Okay, so that's how we do logistic regression. So this right now is an age-adjusted model. I'm going to call this my crude model. A true crude model wouldn't be age-adjusted, but we're just going to use this as our basis of comparison to see, because we want to adjust for age anyway. Now we're going to see, does adding cholesterol status, weight status, and blood pressure, are they actually confounding the relationship between smoking and the outcome? Okay, so right now all we've adjusted for is age. This is kind of like where we're starting as far as saying, okay, this is the overall effect of smoking, only taking into account age, not anything else to do with risk factor, any other lifestyle factors. It's just age adjusted. Okay, so remember what some of these, and this is why I had you paste the output, because I wanted you to be able to compare the odds ratios that you get. But let's just remember this: 3.716, 3.1, 1.5, 1.9. Okay, if I have to, I'll rerun it. Okay, so now I'm going to go back to my homework. So hopefully, actually, I could just. Oh gosh, I didn't mean to do that. Okay, I'm going to go back to my code. Okay, so all I wanted you to do for this part 4 was to run this model and paste the output. And then once you paste the output here, you're going to do a second model. and this is where we're finally into Dan's question. Perform a multiple logistic regression model of the age and risk factor adjusted association between smoking status and being alive versus dead, where the outcome of interest is alive. Okay, so now we already have smoking status and age in the model, and we're adding to it blood pressure status, cholesterol status, and weight status. But again, we have 5,000 some cases here, so it's fine to be adding all these variables. So I'm going to run this. Back to my SAS setup. And this is kind of how we proceed in analysis. We do our, I may have started with a purely crude, but don't forget, we already know what the association of smoking is with outcome. We did that with the 2x2 table. So now I have my kind of like base model, which is just smoking and age. Now I'm adding to the model these other covariates, these other potential confounders. So I'm going to run this one. And now, what I'm really interested in, and I know you're interested too. Okay, now I've got these odds ratio estimates. Where's the raw coefficients? Okay, so up above here, this is the actual beta coefficients. And as I mentioned several times in the lectures, the beta coefficients are not directly interpretable. They're in terms of the log odds of the event of interest, which doesn't really, not very useful. So I go straight to the odds ratios. If you want your p-values, they're here, okay? But if I want my odds ratios and confidence intervals, I actually get more interested in, you'll see them here, okay? So what I end up with is a bunch of odds ratio estimates for each of the covariates. I've got having high blood pressure versus optimal, and normal versus optimal. And this is not important for the homework question, but notice that these ones are actually below 1. Okay, what that means is that they protect you from being alive, which is not, because our outcome is living, not death. Okay, so since these point estimates are below 1, you have a lower odds of living if you have high blood pressure versus optimal. You have a lower odds of being alive, being normal versus optimal. Don't forget, optimal is optimal. That would be the, so I'm not sure why normal. Optimal apparently is better than normal. But really what I was interested in here for the question was, did my estimates of the relationship between smoking and the outcome change? Were they attenuated? Did they disappear when I adjusted for everything else that I identified as potential confounders? Notice I also threw in cholesterol here because I didn't want to give away the answer for the earlier one, but it's also still reasonable. I might still want to be, even though it's not a potential confounder, I may still be interested in the effect of the independent effect of cholesterol. Okay, so really the question, to get to Dan's question as well, is this, did it change the coefficient? Okay, and it doesn't look like it did, because it's 3.73 for non-smokers versus heavy, and it had been, oh shoot.
It was
Something,
3.716.
okay, it barely changed that, okay? Even though I added blood pressure, cholesterol, thank you, Dan, and weight, that estimate didn't change at all. Dan, do you happen to remember what it was for um, light versus heavy?
Yeah, I wrote it down here. Light it went from 3.107, and then adjusted for all those factors went down to 2.906. So
Okay.
I don't see that as a huge difference
Yeah,
either.
right. So it's still very much the same effect. It did go down a little bit, but overall, these effects are remaining about the same. So the take home with that, or what this means is smoking is an independent risk factor for death. It's not because it's associated with something else. It's not because of its association with blood pressure. It's not because of its association with cholesterol or because of its association with weight. Actually didn't have an association with cholesterol. But it's not like what I was modeling was actually capturing something else about the person as a proxy, right? So if smokers disproportionately were, for example, if smokers were disproportionately hypertensive, it could have been when I was looking at smoking by itself that what I was really measuring was hypertension, right? So because they're disproportionately hypertensive, what I was picking up on was their hypertensiveness, not their smoking. So when I put it in the multivariate model, I'm able to isolate the effects of the independent effects. Okay, so smoking, and also important here is notice that the confidence intervals for all of these risk estimates are above 1, meaning even if you account for sampling error, my confidence intervals are all above 1, meaning that it does not contain the null value of, which would be 1 here, because a relative odds ratio of 1. I don't want to confuse you there. It's statistically significant. And I could tell that by looking up here at my p-values. Smoking status, all are less than 0.05. Heavy, light, non-smoker, okay. Having high blood pressure also, I mean, this wasn't a question, but also having high blood pressure is an independent risk factor for early death, independent of its association with smoking. It doesn't look like cholesterol holds up. Weight status does. Okay. So, but that wasn't the question. But I mean, you may as well look at those things as well while you're in here, okay? So a multivariate model is really a powerful tool to adjust for the effects of other factors, okay? And the meaning of the coefficients and the meaning of the odds ratios changes a little bit when you put in other variables, because it's saying after taking into account age, blood pressure, cholesterol, and weight, smoking has this effect on outcome, okay? Or it has this, you know, and likewise, you could say the same thing for blood pressure, taking into account smoking and cholesterol and weight status. So that is, let's see what number 5 actually says then. It asks you a question. Okay, so comparing the results from the age-adjusted model in question 4 to the age and risk factor adjusted model in question 5, does the relationship between smoking and longevity appear to be confounded by the other risk factors? I think we I hope I was clear. That is the effect of smoking diminished when you adjust for cholesterol, weight, and hypertension? And then I told you to compare the odds ratio estimates, just like we just did in the, compare the odds ratio estimates for non-smoker versus heavy smoker in model 4 and 5. We did that. They were about the same. In fact, for that group, they were almost exactly the same. So it was not confounded by the other factors. And as I mentioned, as I was describing it, we can conclude, therefore, that smoking is an independent risk factor for longevity or death. Or you could say it in the reverse, that if you don't smoke, you're more likely to live longer, however you want to phrase it. But hopefully that was not too confusing, because again, the outcome was being alive. I could have done it as death, but I didn't. I'm trying to be positive. So I predicting being alive versus being a dead. Okay, so that was a very long-winded way of me answering your question, but hopefully that is helpful. And that's kind of how you proceed in doing analysis. And it's just a matter of practice as far as getting used to looking at output and knowing kind of the steps and what's reasonable to include. In this case, given there were 5,000 some cases, I wasn't too worried about having too sparse of data, so I just went for it with those variables. I also didn't have very many variables in the data set to begin with, so we'll look at what we have. All right, so I realize I've used up quite a bit of time here, so I want to open up to more general questions. I see some chats. Is homework 4 relatable to chapter 11? Is homework 4 relatable to chapter 11? Oh, so chapter 11 survival analysis. No. I don't really talk, well, I don't think so. Let me, before I misspeak here. Sorry. So the question that came up in chat was, is chapter 11 needed for doing homework 4? And chapter 11 is survival, right? So no, for one. I just want to make sure I say this right. And no for 2. Nope, it's just question 1 is for linear regression, and question 2 is on logistic regression. So survival analysis is mostly for your edification as far as the homework goes. As terms of the final exam, I may ask you something about hazard ratios being similar to, can you use survival analysis? Is there a regression technique within survival analysis? And the answer is yes. You can do what's called Cox proportional hazard models. And from a Cox proportional hazard model, you can get a hazard ratio, which is similar to an odds ratio, similar to a relative risk. So no, I do not have you interpret anything besides survival analysis. I think it's important that you know that there is this thing called Cox regression that allows you to run models for time to event outcome. And all that was in the lecture on survival as well, but it's not in the homework. And I don't think there's not much, that's the only thing that's on the exam is something about hazard ratios. Any other questions? Anything that would be helpful to know before you go into the final? I will mention it's all true, false, multiple choice. There are no tricks in there. I don't think they're pretty straightforward questions. They're one that if you don't know off the top of your head, it should be readily accessible in notes, and there's nothing that's like a mind bender or anything like that. Anything else? Is there anything that would be helpful for me to post that people need for the exam that isn't already available? Okay. Well, you have the entire week. So